Good evening, everyone. Welcome to the 10th tutorial lecture on social networks. So, today we'll be discussing week 10 assignments from previous iterations of this course. There are 10 questions, and if you have any doubt, you can pause me in between and ask, or else you can ask at the end as well. So, let us get started. So, someone has raised their hand. So, if you have any doubt, you can go ahead and speak up. Is there a doubt from someone? Someone has raised their hand. Someone is saying there's some sound issues. Uh, Hello, am I audible now?
Yes, you are.
Uh, okay, I'll continue then. Let us start with the first question. So the first question it says that in the rich gets richer phenomenon, the node which attracts more connections has you have four options: low degree, high degree, average degree, and does not matter. So in the if you recall, in the rich gets richer phenomenon, nodes which attract more connections, they follow preferential attachment. Preferential attachment, which means that they will connect themselves to nodes which already has is well connected. So therefore, out of these four options, the right answer is option B, high degree. So a node that has a high degree, that is, it has connections to a higher number of nodes, will in the longer run get connected to even more number of nodes. That is the rich gets richer phenomenon. Okay. Moving on, coming to question number two, choose the correct option based on the given statements. So you have two statements. Statement one, a disease spread depends on whether the network is sparsely connected or densely connected. So, and a disease, and statement two is a disease spread does not depend on its degree of contagiousness. So, coming to statement one, a disease spread is depends on whether the network is sparsely connected or densely connected. So, if a network is sparsely connected, network sparsely connected, uh, which means it has nodes have low degree, means they are connected to very few neighbors, which means chances of getting influenced or infected is very less. So a sparse network means uh, spread is less, and a dense network means spread is high. So statement one is definitely correct. A statement diseases spread depends on whether the network is sparsely or densely connected. So statement one is correct. Now if we look at statement two, a disease's spread does not depend on its degree of contagiousness. So from common sense we can say that this is incorrect. Why? Because very let's say a viral fever which has a high degree of contagiousness that it can spread easily from one person to another. For such a disease, it will spread rapidly from one node to another in the network. But a disease that has very low contagiousness will not spread, will have difficulty in spreading from one node to another. But here, the nodes represent the people in the social network. So therefore, this statement is not correct. Statement two is incorrect. So the right answer is statement one is correct and statement two is incorrect. Moving on to question number three. In the given graph, the probability of spreading a disease from node A to its connected nodes is zero point 0.4. So there are five connected nodes and the probability of spreading to each of the connected nodes is zero point 0.4. If the disease starts from node A, then the expected number of nodes without the disease is. So to find the expected number without, let us first find what is the total number. So this, let's say, expected number of nodes without the disease, let us call it E. So E is basically what will E stand out to be. E would be basically 5. That that is the maximum number of nodes that can be infected with the disease minus the expected number of nodes. Let us call it EA. That this is expected number of nodes with disease. So let us try to find what EA will be. So EA, if we look at the graph, would basic. So let us first call this EA is an expectation of a random variable. So let uh, XA be a random variable denoting uh, number of infected uh, infected nodes from A. So EA is basically the expectation of X of A. Now X of A is the sum of the random variable XD plus XC plus XD plus XE plus XF. So these all represent that a random variable denoting whether B is infected or not. So XD can is a indicator random variable and takes values 0 and 1. 0 and 1. So 0 means B is not infected and 1 means B is infected. And the same applies to XC, XD, XE and XF. So to find the expectation of XA by linearity of random of this expectation operator, we can write E of XA is basically E of XB plus E of xc plus E of xd plus E of xe and E of xf. Now all these x, b, xc, xd, xea, xf, they are indicator random variables and their expectation is basically their probabilities. So the probability of the expectation of xp is basically E of xp is basically probability that B gets infected, and that is equal to zero point 0.4. So, and all of them, E of xp, E of xc, E of xd, E of xc, and E of xf are same. So basically, this is zero point 0.4 into 5, that is 2. So E of xa is 2, which is what we are calling E of A. So this is equal to 2, and therefore our E, that is the expected number of nodes without the disease, is 5 minus 2, that is 3. So the right answer is option C, 3. Is that clear to everyone? Okay, so we'll move on to the next question. Okay, coming to question number 4, in the branching process, the reproductive number are not if the disease persists in the network with some positive probability is. So, in a what is a branching process? Just to recall, branching process is that uh, you have one node and it is connected to k. It has k children. So there are uh, k children, and each of the children will have again uh, each child will have k more children. So basically, it is a branching process. Looks something like this. This is k, and k, and this continues. So what the question is asking is, in a branching process, the reproductive number if the disease persists in the network with some positive probability. So disease persists, it means that let us call this level. So level 0, level 1, level 2. So in the limit, it this the term disease persists means in the limit uh, n tends to infinity, there is at least one node in level n with the disease. So that means that the disease is still persisting in the network in the branching process. So this is the definition of disease persisting. Now let us come to the question where they are asking about the reproductive number. So reproductive number R naught is equal to P into Q. Basically, what this means is expected number of children of a node getting affected by the disease. So for so in level 0, the number of uh, uh, people affected is 1. In in level 1, the number of children of this 0th node that will be affected by the disease will be P into K. So P is the probability of transmission of the disease from the parent to the child, and K is the number of nodes in this level 1. So PK number of nodes on level 1 is expected to be infected by the disease. So how this PK term comes from the similar way in as I solved in question number 3. So these are the P's. So point 0.4 are the P's and K is the number of children. So here there are 5. So B, C, D, and E and F. So these are the total. They make 5 children. So K equal to 5. And the expected number, as you can see, we found out 0.4 into 5. So this is your P and this is your K. So that is how the expected number of children that would be infected. Now coming to level 2, in level 1, PK nodes have been affected and each of the PK nodes have K children out of which only PK will get affected. So coming to level 2, the number of affected children would be PK in PK square. So for each affected node, PK nodes will be affected and there are PK such nodes on level 1. So it would be PK square. So in level 2 PK square, and if you go on and on, it would be PK to the power n. So in a level n, PK n would be good. Now this PK is the reproductive number. So if P is greater than 0 and K is greater than 0, so if the disease persists in the network with some positive probability is, so if you go this, if the disease persists, it means that pk to the power n is non is positive, basically is positive and greater than 0, is positive and finite. So some, but pk to the power n is, so if pk, that is r naught, is less than 1, then this pk to the power n will tends to 0 under this limit. So in the limit n tends to infinity, pk to the power n will go to 0 if pk is less than 1. So in that case, disease won't persist. So therefore, the answer is if the disease persists in the network with some positive probability, it means that R naught was greater than 1. Otherwise, if it was less than 1, it would have diminished. Okay. Uh, Let us move on to the next question. Coming to question number 5. If there exists a graph G in which there are k nodes in level 1 and every node has k children, the number of nodes in ith level will be. So it's again similar to the for the previous question. So you have a graph G. Let's say it starts with one node, and there are k nodes in level 1. So yeah, 1, 2, 3. So there are k such nodes, and every node here. has k children. So in level 1, this is level 0, let's say level 2, the number of nodes is 1. Here it is k. Here it is becoming k into k, that is k square. And if you carry on, you will see that it is becoming k to the power I. So the number of nodes in the ith level would be in level Li would be k to the power I, exponential growing function. Coming to the next question, question number 6. So, in which of the following models can the disease stop spreading? So, you have two models, SIS model and SIR model. So, SIS stands for susceptible, infected, and again susceptible. Whereas SIR stands for susceptible, infected, and recovered or removed. So in the SIS model, a node can be reinfected. In SIR model, no node can be reinfected. So therefore, it means that in SIR model, eventually what would happen is the ultimately all nodes would be either susceptible or or recovered or a mix. But but you, so basically, let me draw this figure properly. So let's say this blue color nodes represents the susceptible nodes. So you will have a network, and let's say the green represents the recovered nodes. So let's say the connections are, so this is in for the SIR model. Eventually it would lead to such kind of a partition where there are uh, susceptible nodes, and there are a uh, there are susceptible and there are recovered nodes. So you will not have in such a graph, what you will not have is you have, let's say, recovered nodes, and you have some susceptible nodes as well. But you cannot have some infected nodes in between as well. So ultimately, this infection would either lead to will eventually lead to recovery or removal from the network, and therefore uh, this red colored nodes will not exist in the long run in the network. So they will either be recovered or removed, and either become in the following. They will move to the uh, green category, that is the recovered category. So that is how in SIR model, no no nodes would uh, all nodes would be either susceptible or recovered, or a mixture of both. But in SIS model, a node can be reinfected. So therefore, this the red nodes, that is the infected nodes, will continue to exist. So it may not exist all the time, but it will continue to exist. There is no guarantee that the red nodes will vanish. Therefore, in which of the model the disease stops spreading? So a disease will stop spreading when infected nodes disappear. And they will disappear in the SIR model. So only two is the right answer. In which of them can the disease stop spreading? So it is okay. So in SIR, it is guaranteed to stop spreading. So let me write it clearly. So guaranteed to stop spreading, and in SIS, no guarantee. So it can spread or it may not spread. So in such a case, both 1 and 2 will be the correct answer, because if we write only 2, so in only SIR model, it does not, so it says that in SIS model, the disease will always continue to persist, but that is not the case. So it depends on the time of infection, the duration of infection, and the network structure as well. And in certain cases, the infections can stop spreading as well. And in certain cases, the infection can remain in the network as well. So only two will not be a correct answer. So both 1 and 2 will be a correct answer. But in SIR, it is guaranteed to stop spreading. In SIS, it's not guaranteed. Okay. Uh, Coming to question number 7. In the given graph, if nodes A and B are already infected with a disease and the probability of disease spreading from a link is 1/3, what is the probability the disease will not spread till nodes E and F? So what they're saying is that A and B are already infected. So the nodes, so what they are asking, the probability that uh, E and F are not infected. So what is the probability that E is not infected, and what is the probability uh, F is not infected? So let us try to solve this question. So probability probability. Let us call this probability that the disease will not spread till E and F. E would be equal to probability E not infected into probability F not infected. Why we are doing this is because probability of E getting infected and probability of F getting infected are independent events, because E and F do not share any bond among themselves. So there is no bridge or no link between E and F. So the probability of E getting infected or not infected is independent of whether F is getting infected or not infected. Therefore, we can use the principle of independence of two random events, and the probability is just the multiplication of the individual probability. So now the probability of E not infected and probability of F not infected. So these two terms, if you see, they they are basically the same thing. So they are the same thing. So the probability, now let us try to solve what is the probability of E not infected. So probability E not infected. Now if you take a look at the graph, E is connected to D and E is connected to C. So for E to be not infected, it has to be probability of E not infected by C into probability E not infected by D. So again, these are independent events because C and D are not connected in any way. So C can independently transmit the disease to E and D can independently transmit the disease to E. So if E is not infected, so it means that it did not get infected from C and it did not get infected from D. So the probability of E not getting infected from C and D is probability of E not getting infected by C into probability E not getting infected by D. Now again, these two terms, so this probability of E not getting infected by C and probability of E not getting infected by D, these are same terms. So because of the symmetry in the network. So now let us solve these terms one by one. So probability of E not infected by C would be, so now probability, what is the event when E is not infected by C? That can be happen in two cases. So one, that C itself is not infected, therefore it cannot transmit anything to E, or C is infected but still could not transmit the disease to E. So we have to break it into two disjoint components. So in such a case, for if the events are disjoint, we use the sum of probabilities. So probabilities of E not getting infected by C, we can break it down into probability of C not infected, in which case it cannot infect E at all, plus probability of C is infected but cannot transmit. The C does not transmit. Now these two are again also independent event. So when one C is infected, whether it transmits or not transmits to E are independent of each other. So in such a case, we again use the independence of the two events. And now let us find what is probability of C not infected. Probability of C not infected. So A and B we already know are infected. What is the probability of C not infected? Is that it does not acquire the infection from A and it does not acquire the infection from B as well. So that would be 2/3 into 2/3 whole square, because 1/3 is the probability that the disease will spread. Now, if we remove this, now what is the probability C is infected? Probability that C is infected would be basically 1 minus this 2/3, so 2/3 into 2/3. 1 minus 2/3 into 2/3, because this is the probability of C is infected. So C can be either infected or non-infected. There are only two options. Therefore, if the probability that C is infected is not infected is 2/3 into 2/3, then the probability that it is infected is 1 minus 2/3 into 2/3. And And then what is the probability that C does not transmit? Now, probability that C transmit is 1/3, and what is the probability C does not transmit is 2/3. So basically it becomes 4/9 plus 5/9 into 2/3. So that would be 22/27. So this is the probability that E is not infected by C. So that turns out, so therefore the probability that E is not infected would be 22/27, and again 22/27, because probability of E not getting infected by D is the same as probability of E not getting infected by C due to the symmetrical nature of the graph. And if we put it back, what we get is 22/27, 22/27 into again the same thing, 22/27 into 22/27. So the final answer is 22/27 whole to the power 4. So which is actually not given in the four answer. So there is a these options that are given are incorrect, and these options, according to the legend, the right answer should have been 2/3, but this is not correct. This would be valid if they ask for nodes E and F, but if they ask for nodes C and D, but they are asking for nodes E and F. So for nodes E and F, this is the probability that the disease will not affect. So this is 22/27 whole to the power 4. So which is actually greater than uh, sorry, this is what is the probability it will not spread? Yeah. So this is the right answer for this question, which is not mentioned in the four options given below. And if you look carefully, 22/27 is greater than 22/27 is greater than 2/3. So it's 2/3 is around 18/27, whereas 22/27 is yeah. So the probability actually decreases with the probability that will not spread to ENF with the as we move further along away from ENB, the probability of it will not spread decreases, because there are lots of other nodes which are there are more number of nodes which actually can transmit the disease to as we go further along, and hence the probability that it will not get affected will decrease as we move ahead. So this is the this is question 7, and coming to question number 8. In question number 8, if there exists a network where disease is spreading, and once a person recovers from the disease, is still vulnerable to it, so the disease exists. So you can get reinfected by the disease after you get after you recover from the disease. So this is the SIS model. So susceptible, infected, recovered, and then again susceptible. So that is why option 1 is correct. So the disease exists here, only one will be correct. So not both 1 and 2. So in the SIR model, you will not remain vulnerable to the disease once you have been infected. So the right answer is only 1. Coming to question number 9, if the probability of a link to remain open SP and 1 minus P to be closed in a graph. And if at time t the connected nodes get infected, so this represents a percolation model. So this is by definition of the percolation model. So here they do not talk about the recovery or removal of the nodes, only how the infection spreads in a network by means of a link that is either open or closed. So this is the percolation model. Coming to question number 10. So you have a SIS model, and if the probability of spreading a disease is half, what would be the probability that a person who recovered from the disease is likely to get infected? So again, SIS. So this S and this S are equally susceptible. So it doesn't mean that if you become vulnerable after getting infected once, that your vulnerability reduces. It basically means that they will remain equally vulnerable after or before getting infected. So it will remain half. So option C is the right answer for this question. So those were the 10 questions that I discussed. So if you have any doubts regarding these questions, you can ask now, or you can speak up, or you can put it in the chat box as well. Okay, someone is asking for question 1 to 4. Okay, I'll quickly go through question 1 to 4. So, in question 1, in rich gets richer phenomenon, the nodes which attracts more connection has. So, you have four options: low degree, high degree, average degree, or degree does not matter. So, in a rich gets richer phenomenon, the nodes uh, attach themselves to other nodes in the network based on a preferential attachment, which means that a node that already has a higher degree is more likely to attract a new node to itself. So therefore, what happens is the node which attracts more connection has a higher degree. Um, Coming to question 2, so you have two options, two statements. So whether these statements are correct or not. So a disease spreads depends on whether the network is sparsely or densely connected. If a disease spreads on a network, it depends whether it depends on the network being sparsely connected or not. So in a sparsely connected network, what happens is that the nodes have low degree, which means there are very few neighbors that they can pass the disease on to. Therefore, the chance that the disease, it's very less likely that the disease will spread very far in the network because each node is sparsely connected to its neighbors. Whereas in a dense network, it will rapidly spread because every node has high degree in the network. Therefore, disease spread definitely depends on whether the network is sparse or dense. Therefore, statement 1 is correct. In statement 2, it says that a disease spread does not depend on degree of contagiousness. So, obviously, from common sense, this is an incorrect statement because a disease that has high contagiousness, like a viral fever, can easily spread from one node to another. So node represent the people in the social network. It can easily transmit from one node to another. Whereas a disease with low contagiousness will it will be very difficult for that disease to spread from one node to another. Therefore, statement 2 is incorrect. So the right answer is statement 1 is correct and 2 is incorrect. So coming to question number 3, in the given graph, the probability of spreading a disease from node A to its connected nodes is 0.4. If the disease starts spreading from A, then the expected number of nodes without disease is, let us call that E. So the expected number of nodes without disease is E, which can be written as E equal to 5 minus 2. 5 are the total number of nodes that can be infected, and EA is the expected number of nodes that gets infected by it. So the expected number of nodes with the disease. Now let's say XA be a random variable denoting the number of infected nodes from it. And EA is basically the expectation of this random variable E of XA. Now X is a random variable, so it is a sum of five random variables XD, XC, XD, XE, and XF, where uh, XB, XC, XD, XE, XF are indicator random variables that takes value zeros or one. So depending on whether the node is infected or not. Therefore, if we take the expectation of XA, it would, by linearity property of expectation, E of XA would be E of XB plus E of XC plus E of XD plus E of XC plus E of XF. So now for indicator random variable, the expectation is basically the probability of that indicator variable. So probability of XB. So XB is an indicator variable that indicates 1 when B is infected and 0 when B is not infected. So expectation of XB would basically probability that B gets infected, which is zero point 0.4, and which is zero point 0.4 for all the other five as well, as given in the diagram, if you can see. So expectation is E of X is zero point 0.4 into 5, which is 2. So therefore EA is 2, and E, which is the variable that we want to solve for in the question, would be 5 minus EA, which is 5 minus 2 equal to 3. Okay. Uh, Coming to question number 4, in the branching process, the reproductive number R naught, if the disease persists in the network with some positive probability is, so R naught is basically P into K, that is the expected number of children of a node getting affected by the disease. So probability P is the probability which the disease transmits from a parent to a child, and K is the number of children of each node. In a branching process, what happens is you have this level 0 node, you have one node, and in the next level, that node has K children. And in the next level 2, each node of level 1 has K children each. So, and this continues. So in level 1, the expected number of infected nodes is 1. In level 1, the expected number of infected nodes is pk, and in level 2, the expected number of nodes becomes pk square, and up to level n, it becomes pk to the power n. So a disease persists. What does it mean when we say a disease persists in a social network? It means that in the limit n tends to infinity, there is at least one node in level n with the disease, which means that pk is positive and finite. So if pk, that is R naught, the reproductive number, is less than 1, pk to the power n will go to 0 as n tends to infinity, and the disease won't persist. So the disease persists when pk is greater than 1. So the right answer for option question 4 is option B. So these were questions 1 to 4 that I have discussed. So someone has written something in the chat box.
Excuse me, sir.
Yeah, go ahead.
Yeah, Rosanal this side.
Yeah, yeah.
I want to uh, discuss on a percolation model, sir. I have shared here in chat box also.
Yeah, I'm reading it. Just give me 1 minute.
Yeah, yeah. I have some doubt in this question, sir.
Okay, I'll read and get back to. Just give me 1 minute.
Yeah, yeah. Okay, sir. Okay. No issue.
Okay, so you have asked the question, so I'll repeat it for everyone in the discussion. So the question is, in the percolation model, it is possible to find a node, if a node will be infected or not, without any notion of time. So when can you say that a node A is susceptible for infection in a percolation model? So you have four options. So if there exists at least one path with all open edges from the infected node to the node A. If there exists at least one path with one open edge from the infected node to node A, if there exists more than one path with one open edge from the infected node to node A, and if there exists at least one path with all closed edges from the infected node to node A. So let me first draw the diagram, then I think it will be better. I'll be better able to explain it. So, okay, so let us do this calculation. So the question is like this. So you have, let's say, a network of nodes. So now let's say this is your infected node, and let's say this is node A. Now let us consider option one. So in option uh, one, what they says is, okay, so in option one, it says that if there exists a path, at least one path with all open edges from infected node to node A. So open edges means that the disease can spread through that path. So let me draw the open edges. So I'll use the green color to denote open edges. So let's say you have, this is um, okay, this is this is the path. So it means that the disease. So let's say this. Let us call this node N, the infected node. So green means it is an open edges, and means that the disease can move from node N to this node on the left, to then to the right, then below, and then to A. So this green, there is a green path that leads from N to A. Therefore, in such a case, A is susceptible to the disease from N itself. Now let us explore the second option. Second option says that if there exists at least one path with one open edge from the infected node to node A. So they're saying that there exists at least one path with one open edge. So let us say that this. Now let's change this colors, and let's say I remove this and make this a closed edge. So it says that there exists at least one path with one open edge. So maybe I can change this. The scenario becomes like this. So the red path means it is a closed edge, and green means an open edge. So if such a path exists, there exists at least one path with one open edge. So this green there exists. This is a path with one open edge. But in such a case, A is not susceptible to the disease because the disease won't pass from N to A smoothly because the path from end to the node on the left is blocked, that is closed. Even though from the left to the right it is open, it cannot pass from N to A. So therefore A is not susceptible in this case. In option 3, they are saying that if there exists more than one path with one edge from the infected node to node A. So let us draw a few more edges, let's say from let's say let's say from there is an open edge from end to this node, then we have some closed edges here. So it is, let's say, something like this and something like this. So there are more than one path with one open edge from the infected node to A. In such a case, again, the disease won't reach A because of this red line. So there is no green line that reaches uh, to A from N. So therefore, again, A won't be susceptible in such a case. And fourth one, if there exists at least one path with all closed edges from the infected node to A. So obviously, if I let's say okay, so they are saying that we have all closed edges. So in such a case, what would happen is that obviously the disease won't come to it because all of them are closed. So the disease won't spread from end to the left node, to the right node, to the bottom node, to A. So in the right answer is option one. So if there exists, the right answer would be when all of these paths are green. So there exists at least one path from the infected node to A with all open edges. I hope that answers your question.
Excuse me, sir.
Yeah, go ahead.
But node A position or location of the node A is not mentioned in the network. If A will be the next node, just immediate node
Okay,
from the infected node, it means there
yeah,
will be at least one node and one open path.
yeah. In such a case, it will be, but it will.
It
So
it
that
it
is
it
a
may be it may be case of a infected.
yeah, that is a special case. So when in such a question when they have not mentioned your node where A is located, in such a case they are looking for a general answer. So that what you have said is correct. If A is an immediate node, and let's say you take option B, if there exists at least one path with one open edge from the infected node to node A, in that case you're right. A will become vulnerable, but it will not. It will vary from network to network and it will not always be true. It will be true sometimes, but not always. But option one will be true always, irrespective of what the means the structure of the network is, and that applies to all the. So option D will never be correct because the edges are closed. Option B and C will be correct in some of the cases, but option A will be correct always. And in such a question where it is not specified where node A is, they are looking for the best answer, where the answer that is applicable for all such networks. So in you are right that in DNC can be sometimes true, but they will not always true. Therefore, the correct options for this question will be option A.
Okay, no issue, sir. I agree with you. Absolutely right. No issue.
Uh,
But there may be
okay.
one probability from the infected node to immediate node. If we are implementing SIS and SIR model, for example, in case
Yeah.
of a on data set of the corona infected or not infected,
Uh,
how can
can you
we?
can you repeat again?
But
I think there was some network issue. Can you repeat your question once more?
Sir, I am asking, I agree with your this answer, no issue. But I am asking if there is a probability of that node, if a node A is immediate node from the infected node, then what will be the probability
Okay.
of the network? It means it may be
Like,
susceptible or it may be infected.
so it depends on the type of disease also. So whether it is SIS model or SIR
Yeah,
model, uh,
that is different things, sir. That is different things. But I am asking right now, open open edge regarding open edge. If there
wait,
is
let
a
me draw.
if a node A is immediate node of the infected node, then it means there will be one at least one path and one open edge.
Yeah,
Yeah.
okay.
Then in
So,
that case,
so then in that case, so if let's say a path exists like this, so from N to A, so in that case, A is susceptible.
yeah, it means we have take the answer second B option with a minimal condition satisfied and sufficient condition, and option A that is a maximum probability and sufficient condition for that question, as I think.
Yeah, so
We-
right, you're right.
Yeah,
So option,
we have focused with minimal satisfied conditions, sir, for the network. It means we have to
yeah,
choose that path, at least one path, one open edge. It means it may be infected.
yeah, it can be infected. So, but
No,
this is not,
that must not be mandatory if there are more than one edges in the network. If
yeah.
you consider this, sir, I may be wrong, sir.
So
But
I'm saying
if
that option.
if that condition is arise, then what will be?
So that would be mentioned in the question in that case. So it's this is like you said in such a case, this is not a sufficient condition. This can be true, but not a
Yeah.
sufficient condition. But option one is
Yes,
a
sir.
sufficient
Yes, sir.
condition.
Yes, sir. Yeah, I agree with you, sir. No issue. But there is no mentioning of the location of the node A. Okay, in the network, sir.
And yeah, yeah. So
Yeah,
in such a
it may be level 0, it may be level 1, it may be level 2,
yeah, yeah,
and it may be level K, for example, ith level, and so on like
yeah, yeah.
this.
Yeah, so if in
Yeah.
such a question it is not mentioned, so then try to give the answer that is most applicable, like that is most general. So that will hold for all cases, whether it's level 1 or level K, it does not matter. But if it is given, then you can choose B or C as well, if the location is given.
Okay, sir. Okay. Thanks, sir. And one more question also, sir,
Okay,
regarding in this assignment I am sharing in chat box.
okay.
Please see this also. This one, sir. Have you received this?
Yeah, I can see it in the chat box. So let me read it once.
Yeah. Suppose the basic reproductive number is estimated to be R0 is equal to 1.5 if a vaccine giving 100% immunity is available next time and a fraction V is equal to 0.3 of the randomly selected individual uh, were vaccinated. An estimated of
Hmm.
the new reproductive number would be 1.05, 1.1, 1.2, 1.3.
Just a moment. Okay. So in such a case, so what happens is the answer. So what does reproductive number mean? So reproductive number is basically fraction of um, nodes that get infected. So you that is equal to P into K. So K is the total number of nodes that could have got infected, but P is the probability of infection. So Pk is the expected number of nodes that are infected. So reproductive number is that fraction. Now it is 1.5. Uh, this is 1.5. Now when you introduce vaccination, what will happen is again the fraction of nodes that are vaccinated becomes so fraction of vaccinated nodes equal to zero point 0.3. So number of uh, infected node fraction of infected nodes would become 1.5 minus 0.3, that is 1.2. So this is the new reproductive number. Okay. So 1.2 would be the right answer.
No, sir. This is wrong answer, sir. Right
Uh,
right answer is
what?
right answer is 1.05.
Okay.
I can share a solution of this question also, sir, but we are not getting a solution. We are not understanding how they have solved the question.
This is from which assignment? So this year's question, week 10 assignment.
Yes, week 10, which is already
Okay.
done by us.
Okay.
I can
So
I can share solution of this question also, if you permit.
okay, so share it one.
Yeah, just a minute, sir. Just a minute. Is it visible, sir?
Yeah, I can see it.
Yeah, in question number 5. Question number 5, sir. This
One
one.
minute.
Is it
Okay,
visible to you?
question. Yeah, yeah.
Yeah. Yeah. Answer is A 1.05,
Uh,
and they are solving this question by using uh, uh, it means what is the probability of the fraction? It means vaccinated and unvaccinated. It means 0.3 vaccinated and 0.7 unvaccinated people. Okay. And then they do multiply
okay,
1.5 into 0.7. We are getting 1.05, sir. Answer.
okay, okay,
It means, yeah,
okay,
this is the because only 0.7 percentage of the population, total population is
okay. So
susceptible after vaccination.
okay, so yeah, I get it. So what they are doing is so this step. Okay, let me share the screen again.
Yeah.
So okay, so basically it means the fraction of nodes, number of children that gets infected. So initial, so let us remove this step. So what happens is the uh, fraction of nodes that are now infected is 1.5 of it, and uh, so for every 1.5 nodes, um, fraction of vaccinated nodes, fraction of, so this is 0.7. So this is actually, this is the uh, I reproductive number is not exactly the fraction, it is the expected number of nodes that get infected. Expected number of nodes that get infected. So there were 1.5, let's say, nodes which were expected nodes that were infected, and out of this 1.5 nodes, zero point 0.7 of them, that is 1. Are uh, still capable of transmitting infection. So that is what is happening. That is how you get this 1.5. So I will show it by this branching process. You have this node here, and you have some level 1 nodes. So let's say you have level 1 node. So here 1.5 nodes are infected initially, that is before vaccine. After vaccine, 1.5 into 0.7 are infected, that is 1.05. So basically what the reproductive number is in this branching process, how many number of nodes in level 1 are infected. That is the expected number of nodes that are infected in level 1. That is the answer for the reproductive number, and therefore they are doing this 1.5 into zero point 0.7. So because if there are 1.5 nodes in this level 1, zero point 0.7 of them, zero point 0.3 fraction is already recovered because of the vaccination, and zero point 0.7 fraction is left. Therefore, 1.5 into 1.7 are still infected. That is 1.05, and that is the new reproductive number.
Yeah. Okay, sir. Okay. Thanks, sir.
Okay. Yeah. All
And
right.
one last more question also, sir. I have shared in meeting chat box.
Okay. So given that the number of nodes in a circular network is 1 million, and all the adjacent nodes remain connected, we divide the edges with probability 0.4. What would be the average path length of the network? So
There is a circular network, sir, and there are node 1 lakh, and all adjacent node remain connected. if we do rewire the edges with a probability of 0.4, and what will be the average path length of the network?
Mm. So these options are given like they are not in thousands or anything, just 12, 10, 8, and 6.
Yeah. Answers are 12, 10, 8, 6.
So, okay, such a case. Okay, so they are asking average path length of the network. Okay. And let me draw the network.
If we see here, sir, milligram small network experiment, then it will take each letter to an average of 6 hops to reach the destination from
Yeah,
the source to destination. Okay,
yeah,
but here is the probability is 0.4, and the total number of
yeah,
nodes are 1 lakh in the circular network.
yeah, you're right. So we rewire only this uh, edges. So this edges we either
As
keep
I
it or keep.
as
Yeah,
I
go ahead.
think this is not sufficient condition, sir, to find out the average path length of the network. As I think.
Okay. Yeah, I think you have to do this expected path length. So if the path length is 1, what is the probability of that uh, probability? Wait, let me see. So when the path length is 1, what is the probability that the path of length 1 exists is 0.4. When the probability path length is 2, the probability is 0.4 into 0.4. It's 3, it's 0.4 into 0.4 into 0.4. So like this, I think you have to find the expected uh, path length, and uh, that will, I think, give you the answer to this question. So is it coming out to be like that? So it is basically 0.4 plus 0.4 square to 0.4 to the power 1 million. So basically what happens, there are some more steps I think you have to do. Uh, it's one, it's two, 10 to the power 6 into this. Okay, so in that case, you have to solve it out like this. I think I'm not sure. I'll send you this solution by email if you don't mind.
Okay, sir. Okay. No issue, sir. Thank you, sir.
Okay. Okay, so someone has asked a question. So assume you have your own friendship network with numerous friends and call this part of the network as cluster A. There is a cluster B with lot of individuals who are friends. You meet an individual in cluster B, uh, make friends with that individual. This friendship represents, so this friendship represents social influence, direct closure, homophily, uh, weak tie. So this is basically a weak tie, as I can see it.
Yeah.
So
Answer may be weak tie, sir, of this question.
yeah, yeah, weak tie.
Yeah, weak tie. That is the right answer. Okay, sir. Thank you, sir. We will meet in next meeting, sir. Thanks a lot.
Okay. If anyone
Yeah.
has any more questions, you can ask.
And this one, second last meeting, sir. In next week, we have one more meeting also.
Yeah, yeah. So
And
this is second.
examination is going to take place on 29th April.
Okay, okay.
And
On
when
the
we will get internal assessment grading points, sir?
so I don't really know about that actually. So that
Okay.
examination part I have no idea.
Okay, sir. Okay. Thanks a lot, sir. Thanks a lot.
Okay.
One more question is sending to you, sir, students.
Okay, I'm seeing.
Yeah.
Small world networks have small average shortest path and small clustering coefficient. Large average shortest path and high clustering coefficient.
Answer of this
High
question, sir, small average shortest path global and high clustering coefficient local.
small and high.
Yeah, fourth option, sir. Small world network having the properties of small average shortest path global and high clustering coefficient local.
Yeah, so in small world networks, high clustering will be seen. High clustering coefficient is seen because they are more densely connected, and the average and small average shortest path global because they are small in size, the network itself. So option 4 is right answer.
Yeah, yeah.
Okay, so there
And
is
one more
next
question
question.
is, yeah,
Suppose
last
that a
question is
person
asking.
uh, okay, so basically they're asking, so a person T1 gets infected and it transmits the disease with independently with probability 0.64, and he comes in contact with 450 people from the population. So the secondary infections would basically be again like I discussed in question number 4 over here. So question number 3. So it's similar to this question number 3 where A is P1 over here and the probability is 0.64 and the number of nodes here it was 5 and here it is 450. So the expected number of secondary infection is 450 into 0.64 that would um, so that is 288 secondary infections. So
Yeah. Total right answer is 288, sir.
yeah,
For a secondary, expected number for secondary.
yeah. So I think most people have started. Okay, there is one more question. In a friendship graph, if the distance between nodes P and Q is 10, if we create a just to the Watt-Strogatz model given k equal to 2, what is the probability of them being friends for a week time? So actually, these questions are from the next assignment. So these will be discussed in tomorrow's tutorial session. So in you can ask the TA of tomorrow's tutorial session. She will be better able to tell this. I have prepared up till assignment week 10. So these are coming in the future assignment. These are present in the future assignment. So you can ask the TA tomorrow, and or else you can wait till next week. So I haven't prepared. I haven't read about this watch to get model yet.
Okay, sir. Formula for this question 1 upon D parenthesis U comma V raised to power K, sir. Formula will be used.
Oh, okay, okay. So I will have to like look into it myself. So if you can help, yeah. So if someone else who have solved it, okay, then it's right. You can ask the TA tomorrow. So she will be discussing these questions.
Yeah, okay, sir, no issue. And in coming week, we can ask a previous question if we having any doubt, sir.
Yeah, yeah, yeah. You can ask previous week's questions.
Okay, okay, sir. Because that will be last session of social
Okay,
networking course.
okay, okay. No problem.
Okay, okay. Thanks a lot, sir. Thanks a lot.
Yeah, yeah. Okay, so I think we can close the discussion today, and
Yeah,
again we'll meet again next week. So thanks for taking the time to join this tutorial lecture. So all the best for your course.
maybe leave right now, sir.
Y- Yeah, yeah, you can leave.
Okay, okay. Thank you.
Okay, so there is one more question. So you have this code snippet. And what is the number of edges in the graph? So we are creating uh, 10 nodes. We have 10 nodes, and we are basically randomly picking a node U and a node V, and while the then while the total number of edges is less than 10, less than n, you are adding an edge between U and V. So what is n over here? Okay, so you are giving the parameter n to the graph, create graph, and so basically create it will go on creating n minus 1 edges. So depending on uh, what n you give, the answer would be n minus 1, I think. Because here you are not using this function anywhere in the code snippet. Answer is n. Uh, okay, yeah, right. So while it will go one more time. So yeah, you are right. So when it was less, when there are n minus one that is already created, it will enter the loop once again because the while statement is still true, and then it will create one more edge, and then it won't be able to enter the while loop, and therefore, yeah, n edges will be created. You're right. Are there any more questions?